this week we're going to focus on 2 of the 5 different standard groups. We're going to focus on operations in algebraic thinking and then number and operations in base 10. So let's begin with operations in algebraic thinking. There are many different clusters within this group here, so be patient as we go through a few examples of each type, and feel free to email me if you've got any questions. Things in the grade levels are now starting to develop more quickly, and they're starting to be more complex for students. All right, so we know that there are multiple different ways in which we can show single-digit multiplication. So in the middle here, I have 5 times 3, which we know from rote memorization that that's 15. So the first way we're going to show is by arrays. So I've created 5 rows of 3. So we can multiply or add 5 plus 5 plus 5 plus 5, or 3 plus 3 plus 3 plus 3 plus 3, etc. Or we can actually individually count them. The second one is repeated addition, which shows from second grade more into the arrays, or in addition to. So I can add 3 plus 3 plus 3 plus 3 plus 3, or we could add 5 plus 5 plus 5. We could create equal groups. We think of this as 5 groups of 3 in each group. So I've got 5 groups of 3 smiley faces, so we could then count that there are 3, 6, 9, 12, 15 smiley faces. Similarly, you could also do 3 groups of 5 smiley faces. Or we could use a number line. You see on my number line that I've got 5 jumps of 3, or we could do 3 jumps of 5. Take a moment, pause the video, and create an array, repeated addition, equal groups, and a number line to represent 7 times 2, which equals 14. So pause the video, come back, and then we'll go through them. So I've got an array. I've got 7 rows of 2, or you could do 2 rows of 7. We could do repeated addition. 2 plus 2 plus 2 plus 2 plus 2 plus 2, or 7 plus 7. We could do equal groups, so we think 7 groups of 2 in each group. So 2 smiley faces in 7 groups, or we could do 2 groups of 7 smiley faces. Further the number line, we can do 7 jumps of 2 or 2 jumps of 7. Using the digits 1 through 9, at most 1 time each, so you can only use the numbers 1 through 9 once. Try to fill in the blanks to make the following problem true. Sarah planted blank blank carrots in her garden. She planted them in blank rows, and each row had blank carrots. Take a moment, pause the video, see if you can't come up with something that might work. Here is one possible solution. There are many because we have the options of using the numbers 1 through 9. Sarah could have planted 24 carrots in her garden. She would plant them in 3 rows, and each row had 8 carrots. Or we could still do the 24 carrots in her garden, but we could do 8 rows of 3. Lots of options. You could do 18 carrots in her garden, 9 rows of 2 carrots, or 2 rows of 9 carrots. Many possibilities. Suppose there are 4 tanks and 3 fish in each tank. The total number of fish in this situation can be expressed by 4 times 3, which equals 12. Describe what is meant in this situation. 12 divided by 3 is 4. And describe what is meant in the situation. 12 divided by 4 is 3. So the first one, there are 12 fish altogether. We know this. If we put 3 fish in each tank, there will be 4 tanks. just like the picture shows below. Note, this is a measurement model of division. The number of objects in each group is known, and we are determining the number of groups. Describe what is meant in the situation 12 divided by 4 is 3. There are 12 fish. If we want to partition or share them equally among 4 tanks, there would be 3 fish in each tank. This is a sharing model of division. The number of groups is known, and we are trying to determine the number of items in each group. Allie has 18 markers. Her teacher gives her 3 boxes and asks her to put an equal number of markers in each box. Caliber has 18 markers. Her teacher wants her to put 3 markers in each box until she is out of markers. What is happening in these two situations? How are they similar and how are they different? So, both problems are about students putting 18 markers in a box. Allie has 18 markers and Caliber has 18 markers. So, taking a look at each statement and comparing each particular piece of the situation, it says for Allie that there are 3 boxes and Allie will put an equal number of marker in each box. Versus Caliber is putting exactly 3 markers in each box. We need to know how many markers are in each group of boxes, and Caliber, how many boxes of markers will we need? Allie's statement, how many in each group? How many groups for Caliber? Let's figure out how many markers Allie should put in each box. Figure out how many boxes Caliber should fill with markers. Let's model with Allie. Here we see we need to put an equal number of markers in each box. So I'm going to take 18 and keep sharing them until I get an equal number of markers in each box. I see that I would need 3 boxes, and each box would have 6 markers in them. Versus Caliber, we want to put 3 markers in each box. So I will partition out or share 3 markers at a time, count them out, until I get an equal number of boxes. So with 3 markers, she would need 6 boxes to fill. Allie is partitioning into groups. Caliber is forming groups. Or we could count. So assume 3 markers in each box. We could count 3, 6, 9. Well, that's not quite 18 yet. So then we'll try 5. 5, 10, 15 markers in each box. Not quite 18. What if we tried 6 markers in each box? 6, 12, 18. There we go. There are 6 markers in each box. Let's count with Caliber. We know that we're going to put 3 markers in each box. So we'll count 3, 6, 9, 12, 15, 18. We counted 3s 6 times. So there are 6 boxes of markers. Another option is known as the inverse operation. 18 divided by 3 is how many? We know that multiplication is the inverse of division, and we know that 3 times 6 is 18, so the what must be 6. We could use multiplication facts and properties of operations as well. So 3 times 5 is 15, and 3 times 1 is 3, so 5 plus 3 is 18. Therefore, 3 times 6 is 18, and there are 6 markers in each box. A little more explaining with this problem. What they did here was take 6 and decompose it into 5 and 1. So 3 times 5 is 15, and 3 times 1 is 3. Then adding their respected totals, 5 plus 3 is 18. That's a play on multiplication facts and properties of operations. So decomposing numbers into something that students may know more easily is acceptable. Even though 3 times 6 would be just as simple to multiply by as 3 times 5 and 3 times 1, but just a different way a student might come up with a more creative way. Another one would be repeated subtraction. So starting at 18, subtract 3, 15. 15 minus 3 is 12. 12 minus 3 is 9. 9 minus 3 is 6. 6 minus 3 is 3. And 3 minus 3 is 0. Because we subtracted 3 6 times, there are 6 boxes. And we could keep track of that by the thought process of doing all that in our head and keep track of that by counting on our fingers how many times we're subtracting by 3. Many problems can be solved in different ways. Decide if the following word problems can be solved using multiplication. Explain your thinking, then solve each problem. So Liam is cooking potatoes. The recipe says you need 5 minutes for every pound of potatoes that you are cooking. How many minutes will it take for Liam to cook 12 pounds of potatoes? Pause the video and see if you can't work through this on your own or come up with some explanation on your own, and then I'll talk through with what I would say. I would say that this could be used by multiplication. We could use this as repeated addition. So 5 plus 5 plus 5 plus 5, 12 times 5 minutes for each pound. So therefore, repeated addition we know is the same as multiplication. So 12 times 5. We could use base 10 pieces to figure this out. 12 times 5 is 12 groups of 5, which looks what I've got there. Based on properties of multiplication, 12 groups of 5 gives the same result as 6 groups of 10. So notice that we took 12, halved it into 6, and then I took 5 and doubled it to 10. And 6 times 10 is much easier to think about than 12 times 5, which may be a rote memorization. So notice that it's the same exact length and we have the same exact pieces, but it's partitioned a little differently. But in either case, the final result would give us 60 minutes for 12 pounds of potatoes. Another problem. Mel is designing cards. She has 4 different colors of paper and 7 different pictures she can glue on the paper. How many different card designs can she make using 1 color of paper and 1 picture? Pause the video if you'd like. Otherwise, we'll go on to the solution here. This one can be solved by multiplication. For each of the 4 colors, there are 7 different picture options from which to choose. So 7 pictures on the first color plus 7 pictures on the second color, etc. This gives us 4 groups of 7, so 4 times 7. Using an array, we can help see a visual representation of the 28 possible choices. Note that the pictures could be different. Note that the colors could be different, but this gives one example of what it might look like. So we could add 4 7 times or add 7 4 times. We could individually count them as well. Nina can practice a song 6 times in an hour. If she wants to practice the song 30 times before the recital, how many hours does she need to practice? This would be a division problem, since the number of hours needed can be determined by counting the number of groups needed to make 30. 30 divided by 6 is how many? However, we can rewrite this into multiplication by asking how many times 6 gives us 30? Well, we know that 5 times 6 is 30. So she has to play 5 hours if she wants to practice the song 30 times. Owen is building a rectangular tile patio that has 4 tiles wide and 6 tiles long. How many tiles does he need? Let's draw a picture to get an idea of what this might look like. We see that it is 4 tiles wide and 6 tiles long, just as the word problem described for us. We can certainly count the number of tiles, but we can also see that our Rectangle is 4 tiles wide and 6 tiles long. So we can certainly count the number of tiles, but we also see that there are 4 rows of 6, or 4 times 6, which is 24. We also could see that there are 6 columns of 4, which also provides 24 tiles. Division can be interpreted differently and can be confusing. So we're going to show pictures or diagrams to help us explain the story better so that our understanding is deepened. So here are 2 different divisions representing 2 different ways to divide, and then we're going to show some pictures about each one. Maria cuts 12 feet of ribbon into 3 equal pieces so she can share it with her 2 sisters. How long is each piece? And then Maria has 12 feet of ribbon and wants to wrap some gifts. Each gift needs 3 feet of ribbon. How many gifts can she wrap using the ribbon? Using tape diagrams can help us. So the first question is asking how long is each piece? So this is a how many in each group type of division problem. So 3 times how many is 12. 3 groups of what is 12 is what we're thinking. So we have our tape diagram. All together we have 12, and we need 3 of how many to get to 12? So I can see that there are 4 in each one. So 4 plus 4 plus 4 gives me 12. So each sister will get 4 feet of ribbon. Therefore, 12 divided by 3 is 4. So 12 put into 3 groups is 4. All right, so the second question is asking us how long is each piece, since each gift needs 3 feet of ribbon, so how many gifts can we wrap using the ribbon? So we want to know how many of each group. Okay, so, number lines, I apologize. Refrain everything I just said. We're going to use number lines instead of a tape diagram. So still the same problem, just using a number line. So we have the number line to 12. We're thinking 3 groups of how many is 12. So how many do we need to hop each time in order to get to 12? That would be 4. So 4, 8, 12. We're hopping 4 each time. Now the second question using a tape diagram. The second question is asking how many pieces does one get, or how many groups do we need? So how many groups of 3 is 12? So this time we know that each subset is 3 in our tape diagram, and we know we need to get to 12. So how many 3's can we break this into? Well, we can do 4 of them. So 12 divided by 3 is 4. Therefore, Maria can wrap 4 gifts. Now using a number line. We need to hop 3 each time. So our hops are 3, but how many hops do we need to make? 3, 6, 9, 12. We need to hop 4 times. True or false statements. So I've got a list of them here, and we're going to talk through each one, if they're true or if they are false. So 4 groups of 5, does that give us 20? True. Is 34 equal to 7 groups of 5? False. 34 does not equal what it should be, 35. 3 times 6, is that equal to 9 times 2? Well, 3 times 6 is 18, and 9 times 2 is 18, so this is certainly true. 5 times 8 is 40, and 10 times 4 is also 40. Notice in this particular one, as well as the previous one, that if I take 5 and double it, I get 10, and if I take 8 and halve it, I get 4. So I'm having one and doubling the other, and still getting the exact same solution. That's also true with the one above. So, not the one above, excuse me. About 6 times 9 and 5 times 10. 6 times 9 is 54, and 5 groups of 10 is 50. False. This one, similarly, students may be trying to do the addition. strategy where if I subtract 1 from a number and add 1 to another number, it still adds to be the same, but notice that it only works if we're halving or doubling in multiplication. All right, so 2 times 3 times 4, is that equal to 8 times 3? Well, 3 times 4 gives us 12, times 2, or doubling it, is 24, and 8 times 3 is 24. So this is true. Notice that on this one, I could take 2 times 4 and get 8. So that's just the commutative property here and decomposing numbers and rearranging them. 8 times 6, is that equal to 7 times 6 plus 6? True. The right side is 7 groups of 6 plus another group of 6. So I actually have 8 groups of 6 on the right, even though it's not written that way. And then the final one, 10 plus 2 is 12 times 4. Is that the same as 40 plus 2? False. This does not follow the distributive property of 4 times 10 plus 4 times 2. So the distributive property being 4 times 10 and then distributing 4 times the 2 as well. Joey had 120 stamps. First, he gave his sister half of the stamps, and then he used 3 to mail letters. How many stamps does Joey have left? We know that when we have halves, there are 2 equal parts. When we have thirds, there are 3 equal parts. So although third graders don't have a grasp on fractions yet and the rules of fractions, we know the halves, thirds, and quarters and what those represent. So if we have 2 equal parts and using a bar diagram, we have 120 stamps altogether. Then splitting that into 2 equal parts, we'd have 60 on one side and 60 on the other. We know that we give half of our stamps away, so we need to ignore half of them, leaving us with 60 stamps left. Of the 60 we have left, we used 3 of them for letters. So how many plus 3 gives us 60? Counting backwards by 3, we can identify that Joey has 57 stamps left. All right, numbers and operations in base 10. So this is a small little standard that we need to cover. So let's start here with some leatherback sea turtles. When thinking about leatherback sea turtles, what could these numbers possibly mean in this context? The number 4,200, 540 to 1540, 50 to 166, 48 to 96, and 2 to 3. So before I even went any further, I just threw out some meanings, and these are possible meanings. These are just certainly not the correct meanings necessarily, just what first popped into my mind when I'm thinking about sea turtles and what I know about sea turtles. So the top number could possibly mean the largest weight. The second number there could be an average weight. The third one, years of life. The second from the bottom, possible days to hatch and number of eggs they lay. Just some ideas, so conversation starters, if you will. So adult leatherback sea turtles, an average weight of 550 to 1,540 pounds. There is a study tracking leatherback turtles' weight about 800 pounds. What will the new range of turtles weights be for this group? So we have an average weight and then we have weights of the ones that they've been tracking. How many different possible weights are there? Explain why your numbers make sense. So let's think about how we can show the weights and the number of turtles. Perhaps we can use a number line and place value chart to help us. So I have a number line from 500 to 1,500. I know that the average sea turtles weigh 550 to 1,540, so I put those dots on the number line. The number in question we're thinking about is 800, so slightly more towards the smaller end. So I've kind of zoomed in on 800 here with a new number line. And I'm particularly interested in the numbers between 750 and 840. So the least possible weight is 750. The greatest possible weight is 849 pounds based on rounding. So our possible weights will start from 750, 751, 752, 753, etc., all the way through 849. So we have a large range that could possibly be from. Rounding is an estimation strategy that uses place value benchmarks. So when I think about the number 784 and we want to round to the nearest hundreds, looking at it in its hundreds chart would be appropriate. So I look at 784 and I've got it placed here on a number line so we can see the number. Notice that 784 is much closer to 800 than it is to 700. And notice when I'm rounding, the range in which we would round to 800 is located in pink there. Numbers rounded to a greater place value benchmark are easier to work with. So rounding to hundreds is easier than rounding to tens. And I've got here a list of them. Look at all the ones that we would round to 800 versus rounding to tens, their step through. So there's many more options when we're rounding to the tens place versus rounding to the hundreds place. And another visual diagram, notice the hump there, we reach the 5 mark and we go either one way or the other. The following leatherback sea turtles are found swimming in the Caribbean Sea. The weights of these turtles are 749, 653, 688, and 704 pounds. Add 4 new weights that could be in this group of sea turtles based on their weights. Explain your thinking using words, numbers, or pictures. Take a moment to pause the video and take a few guesses on what you think and your thought process, and we'll come back together and go over the problem. So when I look at these numbers and rounding them to the nearest hundreds, 749 rounds to 700, 653 to 700, they all are rounding to 700. So you could choose any 4 numbers that would round to 700, such as 702, 748, 675, or 651. Using a number line would help us with this. So I've listed the numbers, the 749, 653, 688, and 704 on a number line. And I put an arrow with all the numbers in which we could choose from. So there are many that we could have chosen from. So as long as your numbers were in this group setting, you would be perfectly fine. How many marbles are in the jar? Maybe you might need a little bit more information than that, since they're not real marbles that we can see. In the jar, there are 216 red marbles and 403 blue marbles. Tom says there are about 600 marbles in the jar, but Debbie says there are about 620 marbles in the jar. Who's correct? What do we think? Let's look at Tom's possible solution. It appears that Tom uses the 100 value as his benchmark. So he looked at the the tens category and saw 1 and 0 and rounded that way. So 216 would round to the nearest 200 and 403 would round to 400. So 200 and 400 is 600. So I look at my number line and verify. So either one would work. That 216 is close to about 200 and 403 is also about 400. Let's look at Debbie now. Debbie used the tens as a benchmark for rounding. Rounding 216 to the nearest 10 is 220, and rounding 403 to the nearest 10 is 400. So she gets 220 plus 400, which is about 620. Verifying on the number line, 216 is about 220 and 403 is about 400 when rounding to the nearest 10. This example shows us that numbers can be rounded to more than one place value benchmark. Further, that rounding numbers are useful for estimating amounts, and we can round numbers to add them more easily, and we can round numbers to get a close estimate. Which 2 jars have about the same number of marbles? How are they similar? How are they different? Pause the video, do some checking with some rounding, come back and we'll talk about it. Rounded to the nearest 100 with each of the jars would give us 400, 300, 400, and 200. Rounding to the nearest 10 of each of the jars gives us 390, 320, 370, and 220. So when I look at them, things that they have that are similar is they have a lot of marbles, and 3 of them have more than 300. They're different based on how we round to them. But it appears that the ones that have about the same number of marbles when rounding to the nearest 100 would be the first and the third jars. Homework. There is a rounding worksheet that I provided in the rounding homework Dropbox area. Complete, scan, and upload back into the appropriate Dropbox area to practice more rounding skills, both to the hundreds and the tens category. There are 6 tables in Mrs. Potter's art classroom. There are 4 students sitting at each table. Each student has a box of 10 colored pencils. How many pencils are at each table? How many colored pencils do Mrs. Potter students have all together? We can reason this through base 10 pieces. So I have 4 sets of 10. Each stick represents 1 student, and each student has 10 colored pencils. There are 4 students, each with 10 pencils, 4 groups of 10, so 40 pencils at each table. That answers part A. Now what I'll do is that there are 4 students sitting at each table, each student with 10 pencils, so I've created 6 different groups for each of the different tables. Here we created a visual representation of the 6 tables with 4 students sitting at each table. But I have a lot of 10 sticks here, so we could rearrange them and group them into groups of 10 because I know that 10 groups of 10 gives me 1 group of 100. So it looks like I can count out 10 of them, and I'll end up with 2 groups of 100 with 4 sticks left over. So 2 groups of 100 and 4 groups of 10 for a total of 240 pencils altogether. We can also reason through this using a number line. So each jump is worth 10. We do this 4 times for each student at the table. So 10, 20, 30, 40. 4 jumps of 10 represents 40 pencils. There are 40 pencils at each table. Well, if I know that there are 40 pencils at each table, then I can count by 40s on my number line 6 times or 6 jumps for each table. 40, 80, 120, 160, 200, 240, making 240 colored pencils altogether with the visual aid of a number line. We can also reason through this using a mathematical sentence. Each student has a box of 10 pencils, which is 1 group of 10. There are 4 students at each table, so there are 4 groups of 10. And that would be 4 times 10, which we know is 40. Moving forward then, since there are 6 tables and 40 pencils at each table, there are 6 tables times 40 pencils at each table in total. This 40 arose as 4 groups of 10 or 4 times 10. So I kind of expanded that 40 into 4 times 10 times 6. So this is written in expanded form here. Using the associative property to help us multiply a little bit easier than 40 times 6, we see that this is the same as regrouping here. 6 times 4, which is 24, times 10, so 240 pencils. We think of this as 24 groups of 10. Let's look at multiplying by a 10 and how it looks when multiplying using the algorithm way that we've learned. So let's look at 9 times 50, for example. We think of this as 9 groups of 50. So here's one group of 50 across the top here, so 10, 20, 30, 40, 50. Then we have 2 groups of 50, giving us, and then now all of a sudden we have 9 groups of 50, so putting them all together. So currently I have 50 times 9. We would know that that would be, we would take 9 times 0 and get 0 in the ones category. Notice we don't have any ones here. They're all a bunch of 10s. Well, then if I have a bunch of 10s, we need to regroup them into hundreds, correct? So now we have 45 groups of 10 that we need to group into 100. And notice on the column there that then we would take 9 times 5 and get 45. So we have 45 groups of 10. So that's what that comes from when we're using the algorithm to multiply. So now I'm going to group them into groups of 100. So 10 groups of 10 gives me 100, or one group of 100. Notice we can make 4 of these, and then we'll have that bottom 5 left over. So across the top here, we've got 4 groups of 100. On the bottom, we have our leftover of 5 groups of 10 for a total of 450.